Hello everyone. Good afternoon. Nice to join me here today in the sharing. My name is Luo Li. I worked at Shopee data infra team. I will go through four parts of my content. The first one, I'm going to introduce the real scenarios inside our company and what challenge we're really facing, and what is the real problem we will have to solve. And the second part is the practice of how we solve the problem, and what achievement we made by just use the new technology like a Flink and Paimon. The third part is the optimization of the open source community itself, because Paimon and Flink is good, but it cannot meet every request we want. So we have to develop it a little bit more to meet our specific request. And the fourth part is the future plan. Okay, the first part is the stream scenario or Shopee. So the first shortcoming of this architecture is we have to maintain two separated pipelines. One is for the bench ingestion and one is for the real-time ingestion. This will also lead us to have to maintain two branches of the code, one for the bench and one for the real-time. This will cost our extra human resource to maintain these two code. This is the first shortcoming. And the second shortcoming is the second is it will also double cost our resource to calculate and process the data from the bench and the real-time pipeline. It will also cost the efficiency, waste a resource. It's not efficient. And the third challenge here is the data consistency problem. Since we ingest the data separately from two pipelines, it is hard for us to maintain the data consistency 100% or absolutely consistent, because it's a totally different pipeline, different logic. But if you want to maintain the data consistency 100%, it is quite difficult. Sometimes it is even important. So we received many complaints from the business side, say that the data is not consistent and they don't trust the data. So this is another challenge for us. And the last one is, as you can see, we update the Hive table to Hoodie table. Actually, we use Hoodie MOR table, but MOR table is also not perfect. We have to Hoodie table must be merged periodically by the background process or background job to save the checkpoint periodically. So it will also cost the extra resource to do the merge task, and also even we have to develop a new system to help our user to manage the merge task and the Hoodie table checkpoint. So this is the first scenario. So we have to improve. The second one is the incremental computation scenario. It's an incremental computation request actually. So the background is like this. In the stream pipeline, the end user might just want the final version of the data. Like for example, if this is the order, some people may only care about the complete state of the order. So it's only care about the final version of the data. But for other people, they only care about the change path of the data. So if we want to do this two bunch of the different requests, it is hard for us to just do it in one. So like this example, since we have the final version of the data finally, it's okay. But we have to cache all the change log, all the delta date in the Flink state in the memory. It will also cost a lot of memory resource of the Flink job. That's the first shortcoming. And also it will also make the Flink job hard to maintain. The job will grow very big, and if it's crashed, we have to rebuild all the things from zero. it will also cost a lot effort to maintain. So in this scenario, what we really need is a changelog things of the data itself to describe and track the data states for the record and for the data. So this is the second challenge we have to deal with. And the third challenge for us is actually a near real-time data analysis request. I will use the dashboard as an example, but essentially it is a near real-time data analysis request. Okay, so when we say near real-time, what do you mean by that is we want our end user need the end-to-end data latency less than 10 minutes. Less than 10 minutes, that's a near real-time data analysis. By doing this, we have to deliver the maybe this right here. This is the BI request or a dashboard portal or some data product, whatever. But the essential request is that it needs to analyze the data. So if we want to deliver the end-to-end latency less than 10 minutes, we have to develop the whole pipeline one by one, because the latency is so less, and the process logic can't be very complicated here. So this will bring us challenges. The first is the data is reused. The data we can't reuse the data in the pipeline between the different jobs. So the data redundancy is quite high because the data process logic here in the job is quite similar, but we have to deliver the matrix or deliver the end analysis layer one by one. This is the first challenge we have to deal with, and also since we have to provide the analysis interface, so we have to rewrite the data again to some query system like a Lakehouse or HDFS. This will also cost the extra storage resource, and also cost more efforts. So what we really need here is a storage layer which can keep update its state and support near real-time analysis. This is the request here. So all the three challenges, all the three scenarios directed to one thing. What we really need is a storage layer which can support changelog and streaming update, and also easy to manage and cost efficient on not just the computing and also storage, and also can work together with Flink. So this is what we really need and we're looking for. Okay, so here we comes to the practice of how we solve this problem. So this is the first solution we come up with. Actually, this is the new data ingestion architecture compared to the previous one. We have many improved points here. The first improved point is we eliminated the bench ingestion pipeline here and replaced it by just a bench initialization job. It is once for all. Whenever we want to ingest a new table from zero, we just need to launch this initialization just once, and after that, all the updates will go through this real-time update pipeline to keep the data update. So we don't have to maintain two bunch of the code. We just maintain one code, and it can solve the problem, and it will only cost one bunch of the resource. This is the first point we improved. And the second point is we update the Hoodie MLR table. By doing this, we don't have to merge the MLR table from Hoodie periodically. It will save the merge task resource. And also, thanks to the Paimon fantastic feature, we can provide the end user the full table view of the table and also the changelog of the view of the table. Depends on how people want to use the data. Okay, so this is the second point we improved. And also by doing this, since the pipeline is quite simple, we can deliver the end-to-end latency less than 10 minutes. And also compared to Hoodie over here, we can save, as our observation, we can save like 40% of the computing resource and 10% of the storage. What we do is to decouple the data to several layers on Paimon, and by doing this, we can reuse the data at each layer, and we can aggregate the data at each layer. So by doing this, our data flow from step to step will reduce significantly. So by reuse the data from each layer, we can save time and reduce the complexity. And also we can save more than 50% of the computing resource. And also, since the data flow is reduced step by step, we can deliver the end-to-end data latency. There are more different. There are more secret at this solution. So I will also use the task diagnosis as an example. So since we can decouple the data from layers, we can at each layer we can define a time window and define many metrics and calculate the values in this step. So at each step, we can know what exactly happened by monitoring these matrices. So at each step, we can just monitor this diagnosis result to say to monitor what is going on, or whether it is the potential risk in this step. And move to another step, we can do the same. We can define a new data window and calculate the new data matrices and the values, and monitor the new matrices to send the diagnosis log or conclusion. So yeah, so by aggregating the matrix step by step, we can reduce the data flow by 10 times at our experience. Okay, so also if we want to monitor the path, or we want to analyze do some offline analyze, we can also write the data to some other systems downstream. So this is the second solution we come up with to solve the near real-time data analysis. Okay, this is our practice. The third, you can't move anymore. This is the practice we actually try to improve our system and meet our business request, and also we also do some community open source community activities to improve the Paimon and the Flink itself, because the system can not always meet our request perfectly. Yeah. The third part I want to share is the optimization we did for the Paimon itself, because it's not always meet our business request perfectly. So sometimes we have to do some improvement by ourselves. The first background is the first business request is like this. The background is like this. From our finance business team, they want to save a data checkpoint for each day for some compliance request or some other business request. But at early days, when we use Hive table, what do we have to do is to scan the previous full set of the data and for previous date and the delta date of the current date, and merge it together as a new checkpoint to store it at the Hive partition. A separate. Our solution is just simple. So we update our data format from Hive to Paimon. And we developed a feature to let Paimon automatically generate a Paimon a branch based on the event time of the date. So each day, the Paimon will cut a new branch on Paimon for the data, and we don't have to merge the data again and again.